What up, algebra people? All right, so this is the first time I'm doing this where I'm recording the lesson and posting it to YouTube, and I figured I'd do a lesson we already have done in class. And so this way I can just practice, and if you want to look at the notes again, you can. This is 9-1, Properties of Radicals. No essential question, we'll just jump right in. Okay, so the first concept that we have going on here, and I don't know what this thing is that's here. But, oh, nice. There's a thing right there. Cool. All right, well, it's out of the way now. Okay, so remember, expressions don't have equal signs. Otherwise, they'd be equations. The sign, this little sign right here, which looks like an R, means radical. So what we're doing here is simplifying radical expressions. And we're going to start with the product property of square roots. In words, the square root of a product equals the product of the square roots of the factors. What? I don't even understand that. Okay, so it's the square root of 9 times 5. Oh, multiplication. That's why it's product. Property of, oh, square roots. This is a square root because there's no number here in the root. So that means it's a 2, which is a square root. And all this means is that we can break this square root with two factors into two separate square roots. We can evaluate the square root of 9, which is 3, and this is written as 3 root 5, which means 3 times root 5. So I've already set these up for you. Square root of 108 is equal to the square root of 36 times 3. Now, why in the world did I write 108 as 36 times 3? Because 36 is a perfect square. So this is really hard to write on, so I'm going to be really bad at it. But using the product property of square roots, I can break this square root into 2. Oh, that looks great. Oh, it's so good. Oh, and you still understand it, which is the best part. And the reason we've written 108 as a product of a perfect square factor in 3, right, is because we can take the square root of 36, which is 6, and now we can write this as 6 root 3. This thing's like flashing. It's so cheesy. Okay, so now looking at the square root of 9x to the third. Well, that's the same as 9 times x squared times x. Now you might be going, okay, 9's a perfect square, so when we use the product property of square roots, that's simple. I get the square root of 9. I know that's going to end up being 3. Oh, look at that. Oh, the quality. The quality here, guys. Oh, it's terrible. Okay, x cubed. Okay, I don't know if you remember the product of powers property, but we have a power, which is a combination of a base, x, and an exponent to the second power. When you're multiplying these, right, you would keep the base and add the exponents. And when there's no exponent, it's 1. Why did we write this as x squared times x to the first? Because, of course, we can take the square root of x squared. Oh, nothing but the best technology from PYLUSD. Let me tell you guys. Oh, it's so good. There we go. All right. So anyway, the point being that square root of 9, well, we'll just put that as 3. The point being that this is x, the square root of x squared. Now, if I have a little space down here, just to remember what this actually means, is that if you have a raised to the b over c power, so you have a rational, this thing's awesome, then you get this. You get, oh gosh, this thing's awesome. Okay, you get the c root of a to the b power. Okay, what does that have to do with this? Well, see this? X is a, squared is b, and this is 2, remember, because we're taking a square root? So really, this thing can go backwards to here. That's x squared divided by 2, which is the 2 out here, and 2 divided by 2 is 1. And because it's so hard to write on this thing, I'm not doing very well, but this is essentially x squared over 2. Oh my gosh. It actually doesn't work. This thing has no fidelity. So anyways, you get 3x. How beautiful is that? And you are done with that particular example. Let's keep on going. I know this is really bad, but that's because I'm trying to learn how to use these tools. They are not very good, but, you know, so be it. This is the way it has to go. You guys can handle it. I'll handle it too. Okay, how about this beautiful new property? The quotient property of square roots. Okay, square roots. Yep, these are square roots. Okay, sweet. All right. Quotient property. That means that we're doing what operation? Dividing them. So the square root of a quotient equals the quotient of the square roots of the numerator and the denominator. Okay, so we have 3 divided by 4. Yep, that's a quotient because you're dividing. And you're taking the square root of the whole thing. That can be broken up into square root of 3 over the square root of 4. Beautiful. I think we can do that. So the algebra, which I did not go into on the last one, says when you're doing this, the square root of a over the square root of b, my pen stopped working. Okay, we can break that using the quotient of property square roots, so we can write that as square root of a divided by the square root of b, where a is greater than or equal to 0, and b is greater than or equal to 0. Okay, why do they have to be greater than or equal to 0? The issue is that you cannot take a square root of a negative number. I don't know if you guys remember this, but if you take the square root of a negative number, you leave the real number system and you go into the complex number system, which we've discussed in class. And so there's no way to take a square root of a negative. These numbers have to be either 0 or positive. And in the case of b, actually, b can't even be 0, right? Because if you take the square root of 0, that is 0, but then we'd be dividing by 0, which opens up a whole nother can of worms. Okay, we covered that in class, so I'm just gonna move on. But we have the square root of a fraction. We can break that into the square root of 15 over the square root of 64. Okay, this is obviously working. Oh, it's a beautiful 4. Okay, square root of 15. You can't take the square root of 15, so we're just going to leave that as the square root of 15. And the square root of 64 is 8. So there's nothing else we can simplify there. Same thing here. We use the quotient property of square roots. That means we have the square root of 81 over the square root of x squared. And you get 9 over x. Cool. All right. Well, these same ideas, the product and quotient properties of square roots, can be extended into cube roots. And so, because I have a limited amount of time to record these things, I'm going to have to just blow through this. You can extend product and quotient properties of square roots to the radicals such as cube roots. When using these properties of cube roots, the radicals may contain negative numbers. Unlike square roots, I couldn't take the square root of a negative number, but I can take the cube root of a negative number. And it's going to end up being evaluated as a negative, right? So I'll put that negative there to wait. And now I have to think, okay, cube root of negative 128. Well, let's think about the number 128. 128 is not a perfect cube. And I know in class what we did is we wrote a bunch of our perfect squares, and I'm only, oh, Jesus, oh, it's so good. The technology. Okay, perfect squares. 0 is a perfect square. 1's a perfect square. 4 is a perfect square. Oh, it's so beautiful. 9's a perfect square. Whew, this is hard. 16's a perfect square. 25, how am I doing this? Okay, 0 squared. 0 times 0 is 0, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, so on and so forth. Well, perfect cubes. Let's think about our perfect cubes. Once again, 0 is a perfect cube, because 0 cubed is 0. 1's a perfect cubed, because 1 cubed is 1. And then the next perfect cube is 2 cubed. 2 times 2 times 2, which is 8. And then you have 3 times 3, which is 9, times 3, which is 27. So 27 is 3 cubed. And then you have 64, which is 4 times 4 times 4. And then finally you have 125, which is 5 times 5 times 5. And this goes on and goes on. Okay, the point is here that we have to find a perfect cube factor of this. Because if we have a perfect cube factor, then we can use the product property of cube roots, and we can split it up. So it turns out, and I'll keep the negative even though we know it's going to be negative, 64 times 2. And as you can see, 64 is in this list of perfect cubes. It would also be in the list of perfect squares, but because we're taking a cube root, it's the 64 as a perfect cube that matters to us. Why? What is that? Well, it's negative 4. Negative 4 is the perfect cube of negative 64. Here's me breaking this thing apart using the product property of cube roots. So this evaluates to negative 4. The cube root of 2 cannot be evaluated. It's an irrational number, and so we're going to leave it like that. Okay, you could do the same thing with this, and I'm going to leave this one to you guys just because I only have so much time to teach this. 125 is a perfect cube, so when you use the product property of cube roots, you're going to get a 5 out of that. The x to the 7th is a little more complicated, and maybe I should show you guys that, which is, remember, the root is the denominator of the rational exponent. Let me make sure you remember that. So if I have a to the b over c power, the denominator of the rational exponent, that is the root that you are taking. So 7 is b, 3 is c. You can't divide 7 by 3. However, you can divide 6 by 3. And 6, x to the 6th times x to the 1st is equal to x to the 7th. So when we use the product of cube roots property, we get 1 cube root of 125 times the cube root of x to the 6th. And oh, look at all the room I've left myself. Times the cube root. Oh, I'm going off. I don't even care. I don't care. You can't stop. Oh, you can't stop a freight train. Okay, so the cube root of 125 is 5. The cube root of x to the 6th, that's 6 divided by 3, as per our rational exponent rules. 6 divided by 3, or 6 divided by 3, and that's 2. So that's x squared. And then the cube root of x. And this is it. This is as far as you can go. You are fully simplified. And that's what we're doing in this section. We simplified that radical expression, and my pen stopped working entirely. Okay, now this I'm just gonna have to go super fast. I'll do rationalizing the denominator as a separate video. I'm just making this call on the fly. Okay, cube root of y over the cube root of 216. So beautiful. Okay, let's think about this. What did I just use? I took a quotient, something that was being divided, and I split it into 2 cube roots. That's the quotient property of cube roots. I can't take the cube root of y. I'm just going to leave it like that. But if you extend out our perfect cubes, I stopped at 5 times 5 times 5. Well, 6 times 6 times 6, the very next number in this list would have been 216. Oh, look at that, incorporating the dots. Woohoo! Sometimes people were born to do this job. All right, so I get the cube root of y over 6. I'm now down to a minute to finish this video. Oh my gosh. Can't he do it? Can't he do it? Oh, I should say, do you see all this? Simplify everything inside your cube root or your square root or your root before you start using the properties. That sentence I just said was really important, and this example doesn't incorporate it, but some from the homework will. Okay, I can't go over that now. This is the cube root of 8 using the quotient and the product property of cube roots all at once because we only have so much time. Ay, buka, no es justo. It doesn't work. Oh, gosh, man. Okay, cube root of 27. Oh! Ugh! Times the cube root of y cubed. Oh, it's so... Oh, that's a 3. Okay, what's the cube root of 8? I'm down to 20 seconds. 2 times... Oh, man, that's going to be 3. If I make that x to the 3rd divided by 3, that's x times the cube root of x. Can he do it? Cube root of 27 is 3 times the cube root of that. That's just y. Woo! And that's the end of this video. I'm going to make a second part that I will post to YouTube. Thank you guys. You're amazing.